I'm Tim Ventura, and we're joined today by Charles Chase, the co-founder, director, and CTO of the UnLAB, a nonprofit dedicated to the development of advanced technologies and products that are good for people, the biome, and that further human understanding. Charles' experience includes over 32 years at Lockheed Martin in aerospace systems R&D, including over 25 years at the prestigious Lockheed Martin Skunk Works division, where he built and led world-class multidisciplinary teams responsible for the conception, development, and market transition of transformative technologies. He retired in 2018 as a senior tech fellow, a distinction reserved for the top 0.1% of technical talent in the corporation. At the UnLAB, Charles has continued developing breakthrough technologies, including executing research grants for DARPA, DSO, the Office of Naval Research, NSF, the Limitless Space Institute, and collaborations with Stanford, Princeton, UCLA, and Technion, among many others. So, Charles, welcome. It is a pleasure and truly an honor to have you with me today. Thank you so much for your time.
Yeah, thank you, Tim. Yeah, it's a pleasure to be here. And I wanted to thank you for all the, the work that you're doing in bringing knowledge out there and having people discuss their work across a wide range and, things that, maybe aren't other venues for or very limited venues. And, just wanted to say how much I really appreciate all the work that you're doing along those lines. I think it's super important.
Oh, absolutely. Absolutely. Well, I do a podcast, but I really view this as activism. It's trying to get people involved and engaged and helping to educate them and give them resources to educate themselves, right? Especially when it comes to these niche issues where it's easy to miss, breaking news. And so with your work, it is so incredibly timely because as I was doing research for this story, I found a ton of material on vacuum energy that you had done back in 2022. So I spent probably about 2 hours going back and forth through some of these videos where you discussed things that I've been covering on other podcasts. So again, thank you so much for being with me today. And I am absolutely going to put links in there so that others will also learn from that. So let me start by expressing absolute awe for your work over at Skunk Works. I think all of us who follow aerospace are in awe of what has been done there. You were a core part of that team developing breakthrough technologies, and that is the creme de la creme of the aerospace industry, right? They're the tip of the spear for advanced aerospace design. So let me begin by asking, what led you to transition from Skunk Works to founding the UnLAB?
Yeah, so at the Skunk Works, I founded and I ran the Revolutionary Technology Programs organization. So our job was to develop the technologies at the tip of that spear. And so our team worked on any sort of technology that we thought would have a significant difference for Lockheed Martin systems. And, so that was really exciting. And so, but the team, we were kind of like a startup inside the Skunk Works itself, I would say. And, but it was going super strong, right? Our fusion program was fully supported. A bunch of different other technologies we were doing were, coming to fruition. We had transitioned several things to recently to Lockheed products, and I had taken on a new role, which was mining the entire Lockheed Martin Corporation for technologies that would be moonshots, things that make a significant difference and that can, change the world essentially. That's always been my job and my responsibility there at the Skunk Works. And I had that opportunity to mine the entire corporation for technologies. And, I kind of had done what I could do. And it all was super positive, but I knew there was more that I could work on and more that I could make happen. And so, I retired and started the UnLAB along with my partner, Kate. And, and so we've been fairly successful as far as, our goal remains exactly the same, is to develop breakthroughs that can help the world, but do it really without much of a profit motive or no profit motive.
Mm. That was actually what I kind of picked up when I went through the UnLAB website, and I will put links in the show notes to all of this. I strongly recommend that people visit your website. Again, I'm going to put links into some of the presentations that you've done. You have some absolutely remarkable material. And as I was reading through the website, what I saw with UnLAB is you have a much broader, more diverse vision now than what Lockheed is typically focused on, right? Which is stuff like applied aerospace science and engineering, aircraft and engine design, radar and stealth, weapon systems and ECM, and propulsion technologies. At UnLAB, you're still working with propulsion, but you're also doing more fundamental research into energy and physics, as well as providing fellowships to budding artists and scientists, and developing technologies that have a more humanistic goal of making the world a better place. So you're able to pursue more diversity now, right?
Yeah, so that's kind of interesting because, for example, the fusion program, and I'll say most of the programs that the Lockheed I worked on, I'm not free to discuss, what those are, because of various reasons. But the fusion program, the reason we were working on that was to make an airplane fly for a long time, right? And so developing a compact fusion source for that was what we were after. But we also talked about how that would also provide energy for everyone and would help the world, right? And so, those, now we don't have so much of that dual use, although if you notice, a lot of my funding comes from Office of Naval Research, DARPA. So, with any technology, there's going to be multiple uses. There's, positive, good uses, but you can also use any technology pretty much for, war and defense. So, that's always there.
Well, at the UnLAB, do you have primary focus areas right now? Again, from going through the videos and looking at some of the past speaking engagements that you've done, like one of the big ones that I picked up was vacuum energy as how that applies to both propulsion and electrical generation. That was exciting to me. But you've executed fundamental research grants for DARPA DSO, again, Office of Naval Research, Limitless Space Institute, and you have these university collaborations in place. Have those relationships helped define your focus areas? Are they pushing you in a specific direction in terms of overriding big projects that UnLAB is built around right now?
So I would say it's more the technology that drives the projects versus the other way around. So it's really what is possible, and sometimes what's the adjacent possible. So what are the different pieces that can come together to make something new? And, again, with that focus on, what's good for mankind, what's good for the planet, what's good for the biome, so with that focus on there. And, like you mentioned, a great example of one of our focus areas is generating propellantless propulsion, which has been a holy grail for, a long time and very controversial maybe scientifically controversial, I would say, because the fundamental conservation laws would say that propellantless propulsion, really isn't possible. But, so that's an example of a technology that would have a huge impact. And, it's something I've been working on for probably 20 years, starting back in my time at Lockheed and on to now. And so I think we've really come up with an approach that's going to work.
If it's okay, let me dig into that a little bit. In terms of that propulsion research, one project that you mentioned to me was an NSF grant working on propellantless propulsion, attempting to move the quantum vacuum in a preferential way using asymmetric nanostructures or diodes. And when you describe that, it reminds me a bit of Dr. Charles Buehler and Andrew Rigma's, basically their explanation for asymmetrical capacitance propulsion, something they're working on over at Exodus Technologies, right? Or you could take that back and say maybe a variant on the old Beefield-Brown technology. Is this related in any way?
Oh, it might be, because we use asymmetry both in nanostructures, so create asymmetric nanostructures like optical cavities that are different sizes, different materials. And the theory that we've developed, which is based on just standard quantum theory and standard electromagnetics, so no new physics. It's actually the same formalism that people use to develop the Casimir force and predict what the Casimir force is. So the Lifshitz approach, we're using that approach to predict forces, and yeah, we get forces from nanostructures that are asymmetric. Yeah, and then those are small forces akin to the size of a Casimir force. But then by using a resonant tunneling diode, which is another asymmetric structure, we can generate what we're predicting are fairly large forces because there's a greater asymmetry there. So this idea of asymmetry, whether it's from a potential difference in the resonant tunneling diode or just asymmetry in geometry and material, a lot of people have been pursuing that sort of asymmetry for generating forces, like you mentioned, way back to Byfield-Brown and Brown's work with the asymmetric capacitors that people really like talking about, and it's hard to know what he really measured and did, but so Charles Buehler's work is another example of an asymmetric kind of capacitor configuration. There's other companies out there like I think Hover Incorporated, there's Evo, I believe. There's different companies out there that have these asymmetric sort of structures that are claiming that they're that are measuring forces. Those measurements are really hard to make though because of all the charge associated with that, right? And so you have to be really careful about those measurements, and because the charges can attract to something, and you get spurious forces, especially if you're trying to measure something small. So making something that rotates, it really is the acid test, I guess. But anyway, so yeah, I do think there could be a direct relation between these kind of macroscopic, large size asymmetric capacitor type things, and the asymmetric potentials in our resonant tunneling diodes that we're saying and we predict will generate very large forces. And since they're, on the nano micro scale, you can make an array of these things that's, very lightweight and yet still generates a very large force. But, that all depends on us being able to interact with the vacuum, right? If we can't interact with the vacuum, all the sort of center of mass conservation arguments hold. That, momentum in a closed system has to be contained, essentially. So I think I'm digressing from your question, but
no, vacuum energy is in the news right now. I feel like this is one of those things where, somebody is sending me a wake-up call saying, hey, Tim, this is important. Not only is Charles Buehler's team producing net force without reaction mass in these, again, as you mentioned, larger plate asymmetries, but both doctors Harold Sonny White and Garret Moddel over at the University of Colorado describe converting Casimir effect zero-point energy into electrical power. You just mentioned the Casimir effect yourself. So I wanted to ask if you're also exploring potential energy generation aspects of ZPE, and do you have any thoughts on the emerging science that White and Moddel are working on?
Yeah, so first, let me just say that if you can generate a force like we're predicting from our vacuum fluctuation flow is what we call it, because we're flowing the vacuum fluctuations in a preferential direction. So if you can generate a force, you can make something rotate, and then you can make a generator. So you can generate electricity that way. So, by generating a force with our device, yeah, we'll be able to generate energy as well by using an old-fashioned electrical generator. Um, yeah, and so
Well,
so Sonny and Garret are both really good friends. Sonny and I go back a long time. We worked together when I was at the Skunk Works and he was at NASA. We worked on a few different things that we were both doing at that time. And Garret, I've known for a super long time too. He's come to our advanced propulsion and energy workshops that we've had at MIT there, and I've known Garret for a super long time. Really, really brilliant guy, great researcher. And so with Garret's system, he's using a type of a diode and is measuring a very
yeah.
small current coming from that diode. And so, uh, and then Sonny is distorting the vacuum distribution by creating pillars and things that make the vacuum distribution asymmetric. And because it's asymmetric, you can generate a current that way. So, yeah, both those things look really promising. And time is an interesting component. Like, does it reach, I'm just bringing up things that enter my mind, right? Time is a component there. And does it reach some sort of those type of devices, reach some sort of equilibrium after some amount of time? We worry about that with our own, or think about that with our own device as well. What happens over time with that. These are the sort of things that are at the edge of our understanding of
Yeah.
science, right? With vacuum fluctuations, there's the big difference between what the cosmological constant and QED predicts for the energy density of the vacuum is 120 orders of magnitude different, right? So this is an area of science where science doesn't know really what's going on. And people talk about even with the Casimir force, which we've talked about but never really mentioned what it is. I know you've talked about it on your show before, but when you have two plates that are close together, or other objects, they don't have to be plates. Some of the modes of the vacuum are excluded from in here, some of the frequencies. So there's a lot more outside than inside, and it causes the plates to smack together. You can have different materials. You can actually get repulsion by using different materials on the inside. But what's interesting is you can derive that force, the Casimir force, with never invoking vacuum fluctuations. It's something called radiation reaction, and it's a normal ordering in the quantum electrodynamics. I don't know that much about it. I'm not, I'm an armchair physicist, if anything, and but I do know that this is the case. So, again, that's an example. Are vacuum fluctuations really real or not? And can we use them? What's the, are they mutable? And, what's this difference between the cosmological constant and the value that QED predicts? So I'm just pointing out this is the area that science should be pursuing, and people, the funding agencies, like you've mentioned, like NSF and others, and should be funding this type of work that is in the unknown and is on the edge, and that's the only way breakthroughs are going to happen.
Well, in terms of White and Moddel, as well as what you're doing with tunneling diodes, and what Bueller is doing on a slightly larger scale, in terms of zero point energy, I mean, probably like anybody else who took college physics, right? We all learned about ZPE. We all learned that if you hit the vacuum hard enough with a particle, it'll eject an antiparticle. The basics are all there. But there was always this idea that you can't extract net energy from it. And so to see what they're doing now, I'm like, oh my God, that's amazing. And even more amazing, the part for me that is mind blowing is they're putting it on a chip, which means they can put that into transistor packaging. They can fabricate that like a semiconductor. And so with the tunneling diode system that you're using, in theory, as you refine that, do you think that that's something that you might be able to put on a chip and basically amplify the power thousands or millions of times?
Yeah, so that's the way we make it. We make it just in a regular semiconductor fab, and we do it on a silicon wafer, and you can make an array of diodes, across the wafer, so you can have millions of diodes, all generating forces, and those all add up together, um, and yeah, so that way you can generate with these very micro structures really large forces. And the first application we're looking at is for space propulsion because it's you don't need much force. But as the technology matures, just kind of like Sonny's and Garrett's, they're generating a little current right now. As we understand more about the mechanism and the physics, of course that's going to increase. We'll be able to generate more, I would think. We'll be able to generate larger forces that would have a lot of terrestrial application as well. And like I mentioned, just being a generator and making a magnet rotate, you can generate electricity that way. Everyone could have their own little thing that's generating electricity and, never needs to be plugged in or fueled or anything, right? So sounds kind of impossible. And yet it's, it's all based on scientifically valid assumptions. So, but
Yeah.
it hinges on that one key thing. Is the vacuum something we can interact with? And, and can we consider the universe an open system, which to us it is, it's an open system. So yeah, so we're changing the vacuum and that's going off somewhere. That's someone else's in the universe's problem or issue. I don't know if that makes
Well,
any sense or not, but if
no,
we're sending momentum out by changing the vacuum, well, that's going to go somewhere.
it does make sense. And I want to, once again, point viewers to the links that I'm going to put in the YouTube show notes because you did a presentation. This was a late 2022 presentation where you drilled down on vacuum energy. It was like at least an hour PowerPoint, if I remember correctly. And you went through all of these various aspects of it in great detail, along with the physics. So for people who want to learn more about that, I absolutely want to point them to that. Again, I went back and forth through that thing for a couple of hours doing research, and it was wonderful. It was a wonderful overview. And you talk about propulsion, you talk about energy generation. There is so much substance and information there. Now, I did want to touch on something that's a little bit different, and that's Paul Thibodeau's graphene energy converter. And this one is intriguing to me because from what I have read, this rectifies background energy, but Thibodeau describes it as rectifying Brownian motion, or basically latent heat energy from the environment, into electrical current rather than extracting energy from the ZPE. It almost sounds like these are maybe two aspects of the same underlying constant. I don't know. What are your thoughts on that?
Yeah, so I know a little bit about Paul's work. He gave a talk at one of our advanced propulsion and energy workshops when his first experimental information just came out. I haven't followed too much of that lately. I should see how Paul is doing, but yeah. So I thought that he was thinking that the random fluctuations would happen whether or not you had thermal fluctuations. So I'm not really up too much on where he's at, and but you could imagine vacuum fluctuations, making that graphene move, and then, that causing a little bit of current. He went through a lot, as I remember, to get his paper uh, saying the right things so it would be accepted.
Yeah, yeah, that was, and it was a breakthrough when it came out. I remember
Yes.
reading some news stories about that, and it was mind blowing,
Right, right.
And
So it took some really hard thinking to reconcile what he was observing with the laws of physics.
yeah,
And
and
and and he was able to do that to the satisfaction of the reviewers.
now, without mixing myself up too much, because again, I'm kind of reaching the edge of what my research was able to teach me. But one of the things that surprised me was in Thibodeau's case, there was this idea of rectifying latent heat energy, which is almost like Maxwell's demon or Maxwell's zombies, right? Depending on who describes it as what. And so the idea is that you have kind of a one-way valve for heat energy. More energetic particles based on natural distributions may end up accruing on one side than the other, and you build up a gradient. You build up a current from that, right? And with zero-point energy, what you're describing in diodes sounds similar. I recall this may have been yourself. It may have been Garret Moddel. I don't remember which. Basically saying that electrons can tunnel through some types of diodes, and if you modify the diode correctly, you may be able to generate a net electrical current just through random tunneling, right? They can tunnel one way but not another because of the way the diode is constructed. And again, that idea just grabbed me, and I said, wow, amazing.
Yeah. So, I wouldn't be working on this so hard if I didn't think that there really was something here. And, I've known that for a long time. It's kind of more than just, well, this is scientifically, engineeringly interesting. It's kind of like, I'm driven to do this, and I know that we can make this work. Um, so, but the bar is really high to prove things, right? The bar is really high to prove things. So, I'm really excited about the work we're doing, the work that Sonny's doing, Garrett, Paul, Charles, Encore from Hover, all these people out there working on these devices. And, I think it's just wonderful.
It is. It is.
Yeah.
And it does seem like there's convergence happening. It seems like, at least at the moment, they seem to be converging onto a core set of principles, which I think will help us understand the science better. So let me ask about coherent matter wave generation. You actually have a patent that you received back in 2016. If I remember correctly, you started working on that patent in 2011, and it was actually granted in 2016. And for the lay people in our audience, I want to start out by asking, what is a coherent matter wave? What is a coherent matter wave generator? And what led you to develop this?
Yeah, so I have that patent along with my colleague, Dr. Mo Arman, who was a brilliant Iranian scientist who worked in my group at the Skunk Works. And, he's the one who originally came up with the idea, and then I helped him mature it and, work out some of the aspects of that. So, but what is it? So this is a way of um, making a laser out of particles instead
Mhm.
of photons. So, with a laser, the reason why it's so bright is you've put all the photons into the same phase, into coherence. So they're all stacked on top of each other. And that makes the intensity go up as the square of the number of photons instead of just linearly, which gives you this huge laser sort of power. So we've figured out a way to do that with particles versus photons. Now, particles are what's called fermions instead of bosons, and I don't know, bosons are what photons are. But so being there's something called the Pauli exclusion principle, which doesn't allow you to put two particles that are fermions into the same state, and so you can't make them coherent.
Hmm.
So, um, you know, we've figured out a way using something called the Arhana, and it's crazy because this invention has like, 5 different components that are all a little esoteric that come together to make it possible to make this beam that's a million times more powerful than a laser. Or what I've been most excited about lately is the application to atomic scale additive manufacturing and direct manufacturing, so that you can use this coherent beam that you create by putting the fermions in coherence using the Aharonov-Bohm effect. Um, you can use it to write features down to zero point 0.2 nanometers. You can use it for doing like new sorts of chemistry, because the way to think about this is that the atoms or electrons, which are the particles we're talking about, they're really waves, right? They're
Yeah.
actually waves and have a frequency. And people have shown this, and they interfere with each other. You get interference patterns. People have measured the waves of vitamins and other things. So, particles um, are waves, and so by controlling the phase of those waves using our coherent matter beam device, we can do brand new chemistry that hasn't been possible before by combining the waves. Kind of think of it as a frequency combination
Hmm.
of atoms. And by doing that, like I said, you can do new chemistry, but you can do atomic scale additive manufacturing where it's not, it's like the start of the replicator, right? You'd be able to build something, from its atomic parts into a structure and do that at the atomic scale. At a speed, since it's that coherence and the n squared behavior, you'd be able to do it at a speed that makes it suitable for making devices in a reasonable amount of time that would have a lot of applications. So I don't know if I explained how the coherent matter beam works very well, but I kind of talked about what the payoffs are of that.
Well, no, I appreciate your describing. It's an incredibly complex idea. And so this is one where I would absolutely recommend that people read up on this. I think you had a great description. It's just there's a lot of depth here, right? This isn't like a 5-minute overview type thing. But when I was doing research for that, what grabbed me was this idea of something called atomtronics, which utilizes coherent matter wave circuits, and it can do ultra precise interferometry as well as having applications for quantum computing. So when I read that, I thought, well, I mean, number one, the name Atomtronics is the coolest thing ever. But then I thought, you know what? Not only is he working with vacuum energy, the UnLAB is also revolutionizing quantum computing, or at least has the potential to, right?
Yeah, right, right. So, yeah, those atomtronics, I believe, use what are called Bose-Einstein condensates, which are, at super low frequency.
Yeah.
So the coherent matter beam, um, there's some superconductivity in it to provide mutual inductance, because things to provide the coupling that provides the synchronization of all the matter waves. Um, but we could operate up at liquid nitrogen temperatures, which is,
Mhm.
77 Kelvin. So much easier than the Bose-Einstein condensates that are needed for the atomtronics. And the Bose-Einstein condensates are where you've put particles all into one macro wave function because they're perfectly still. But they're only held still because there's a laser hitting the damn thing that is providing the balance. So I don't know. Anyway, I digress again.
Yeah. Well, you mentioned a moment ago, I hadn't read this. These could be potentially a million times stronger than a laser. So could you use this for something like cutting laser, right? Except you might be able to do nanoscale cutting with it.
Yeah, you can definitely do that, or to do deposition of nanoscale, and again down to sub nanometer sort of dimensions. So, better than anything else that is actually out there, what anything can do right now.
This is like a fundamental tool for developing nanotech.
Yeah, exactly. Yeah, and new sorts of nanotech, and again, new sorts of materials that we can't make now because we're not making the right conditions for those material waves to interfere and combine in a certain way. And so who knows where that leads, and then I don't know. I think about what, can you do it down at for uh, even higher energies, so higher frequencies, and therefore do things like make super heavy elements, right? Another thing I've been fascinated with and, spent some time working on is how to make super heavy elements. These are elements that are way up in the, in the atomic scale that are predicted to be stable.
Mm.
And so, how, atoms that we make that are really with a lot of protons decay, they don't last for a long time. Super heavy elements are predicted to last. And interesting thing is they'll emit positrons.
Well, so you could potentially use a coherent matter wave beam.
Oh yeah, to make these super heavy elements. Yeah, yeah, yeah. But that's much higher energy and higher frequencies. So, I'm not sure if that's even physically possible to do that. But wouldn't that be cool?
That would be, yeah. So let's add that to our UnLAB list is antimatter shielding. And then we've got, quantum mechanical stuff going on. We have a lot. You are working on so many amazing things. Let me thank you so much for your time today. It has truly been a pleasure, absolutely an honor going through all of these amazing technologies with you. Again, the stuff that you are working on at the UnLAB, this is bleeding edge. This is right on the edge of science and technology, and it's so exciting. So for other folks who are as excited as I am, I want to close by asking, how can people get involved with UnLAB and who should be involved with UnLAB? How can they contribute? What are you looking for? What do you need? And how can you assist people?
Yeah, so that's a pretty broad question there. You know, um, I guess I'm really interested in the intersection between energetic ideas and, and science and engineering. So, uh, new ideas are really, really few and far between. And I love hearing um, about new ideas. And it may seem trite, but resources are always needed. But I love hearing from people, so please reach out to me. And I love uh, it's just something about the human spirit that here we all are. With your on your APEC sort of sessions that you hold. Uh, so many people with so many ideas and the energy and the motivation and the desire to further that. And to me, it's just fascinating, this human spirit and the, kind of inherent go that people have to try to discover more, make more, um, and it's just wonderful to see. And, you know, uh, anyone that wants to contact me, please feel free.
Wonderful. Charles, let me thank you again so much for your time today, sir.
Yeah, thank you, Tim. Yeah, it's been a pleasure. And yeah, thanks again for all your great work.